Okay, so now let's just go over the theoretical aspects of this chapter. The first thing is, what is a random variable? It is a numerical outcome of an experiment. For example, if I throw a die, that's an experiment. What are the possible numerical outcomes? Okay, so X will take the value of all the outputs that you can get out of this experiment, which would be called the support. So support is basically all the values that can be taken by any random variable. So the support of X here would be equal to the values it can take. So it's going to be 1, 2, 3, 4, 6, right? Okay, thing is, next question, sum of the values from two dice that are thrown or rolled, okay? So let X be that random variable that has the sum of values from two die. So that would be, the values would be 2, 3, 4, 5, 6, 7, 8, 9, 11, and okay. So that's the sum. The possible sums are like from 2 to 12 because it starts from 1, 1 till it goes till 6, 6. That's the maximum, right? So that is the sum of the values. And this is also called the support of the random variable X, where X is the numerical outcome of an experiment where we throw two dice and we find the sum of the values that show up. Okay. Next thing is, oh yeah, just one more thing that I would want to add in in random variables is there are two types, discrete and continuous. And discrete is in which you can list down the values, and continuous is like between a particular range. So example, I'll just take textbook examples here. So if I say there is a dart board that you have, um, right, and you want, so X would be the outcome of you throwing the dart on the board and getting that value. Like, so it starts from zero, like it goes from 0 to 1, and then there will be values here, right? So there are uncountable values here, and you cannot really identify the total number of values possible. So that will be uncountably infinite, and that is a kind of a continuous random variable. While the discrete random variable was like an outcome, which was 2, 3, 4, 5, 6. Another one that was given in the textbook is if you toss a coin. So n is the number of times you have to toss a coin to get your first head. So that could be from, you could get a head on the first time, you could get it on the second time, and it could go on till infinity. But this is called countably infinite. So you can count the number of times you need to toss the coin to get a particular head. Okay, that's that about random variables. Next up is about the expected values. So the expected values is just I times the probability that the random variable is equal to I, so that the outcome of that experiment was I. So yeah, that is the expected value. Again, the sum of I to n, I times the probability that the value of the random variable will be I. Okay. So next, we'll be looking at a few properties because this has been covered in the textbook and in the lectures. Let's try to find out, if I give you three random variables, what is the expected value of you? So just choose a random variable out of the three. What is the expected value? Okay. So it will be, what is the probability that you can get 1? So we'll just look here in the formula and we'll write it down. So this is going to be 1 times 1 by 3 plus 2 times 1 by 3 plus 3 times 1 by 3, which is equal to 1 plus 2 plus 3. So that's 6 by 3 is 2. So the expected value to get out of the the three numbers is 2. Okay. Next is the properties. So the first one is the expected value of X when you are taking values out of a set A. So set A, so you're taking values from set A, is for C belongs to A, for all C belongs to A, you sum the values of C times the probability that the random variable is equal to C. Okay. And this is called the weighted average. All right. So if you throw a fair die, what is the expected value? Let's try to answer that. What are the outcomes possible? So you have 1, 2, 3, 4, 5, and 6. 6 outcomes possible. What is the, um, you know, the probability of outcome I happening? P of x is equal to I. So that will be 1 by 6. 2 would also be 1 by 6. 3 is 1 by 6. 4 is 1 by 6. 5 is 1 by 6. And 6 is also 1 by 6. So the expected value of x here would be 1 times 1 by 6 plus 2 times 1 by 6 plus 3 times 1 by 6 plus 4 times 1 by 6. Which essentially is 1 by 6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is equal to 18, right? Sorry, so 1 plus 2 is 6, 12 plus 9, 21. No, yeah, so that's going to be 3.5. Okay, so the expected value when you throw a fair die is going to be 3.5. I mean, you cannot get 3.5, but like that is the measure of, you know, what? So it's the expected value that you'll get when you just like, you know, that the values would be around that range. Next up is the next properties that the expected value of addition of two random variables is E of u plus v is EU plus EV. Next, and then another thing is if you multiply a random variable with a scalar value, then that scalar value doesn't impact the expected value except for just multiplies in. So that's E of A, the expected value of AU is A times the expected value of E times U, okay? The next one is, so building up from both these properties, we have E of AX plus BY. Just try to think why do we get this solution? It's very simple. It's very, you know, it's very obvious. So I'll just write it down. Consider AX to be U and BY to be V. So it's going to be EU plus V again, which I can write it as EU plus EV. So that EU now becomes E of AX plus E of BY, which is E of AEX plus B of expected value of Y. Okay, so that's how that is done. Next up is, okay, next is multiplication of two random variables, that is E of UY, where U and V are independent. So make sure you note this. This is V and this is U. Right, so EU can be written as EU times EV. Okay, so the same thing. What is the expected product of the values where you throw two die? So the product of two dies would be EU V, where U is the output in the first die and V is the output in the second die, and hence the product would be EU times EV. So that is 3.5 times 3.5, that is 3.5 square, 12.25. Okay. Next up is variance. Now, variance is the measure of the dispersion of the values or the variability of the random variable. And it essentially is the mean squared difference between a random variable and its mean, and it is written as the variance of U can be written as the expected value of U, the difference between U and the expected value of U, the whole square. Okay, let's write the variance down for X in the die example. So we know that EU is 3.5, right? So the variance of U can be written as U minus 3.5 the whole square, right? And the values possible. So you just like try to write the values here and you find the expected value of the difference. So it essentially is the expected value of the squared difference between the random variable and the expected value. Next up are some questions actually. This would be a property right here. The first one is the variance of u can be written as the expected value of u square minus the square of the expected value. Okay. Next is the variance of cu is c square vu. So let's prove this one first. Okay. I'll write this down as where u is written as expected value of u minus eu the whole square. I just open this value as u square minus 2 eu times u plus eu the whole square. Which can also be written as e of, okay, let me write this down. It can be written down as e of u square. Sorry, this is minus 2 times eu times eu. Why did I write this down? What happened here? Remember that eu is just a scalar quantity. It's a particular number. So you can just use it as a scalar and like get minus 2 eu here and e times u. And the same thing happens again. This plus eu the whole square. I'll write down the two things I did here. E of cu is equal to ceu and e of c is equal to c. So the expected value of a constant scalar is the scalar itself. And if I multiply a scalar with the random variable, then the expected value of cu will be c times the expected value of u. Okay, so this goes right here, and this was used here. Okay, let's continue. I have eu square minus 2 eu times eu plus eu square, which can be written as eu square minus eu the whole square. Like this is minus 2 eu the whole square, and this is plus eu the whole square, so that just negates it. And that's how you have value is equal to eu square minus eu the whole square. Okay, next up is when you multiply the scalar value, how does the variance change? So let's write it down. Var cu can be written as, I'll use green color. I'm just gonna hold it up from right here. Right, that's how you define it right here. So that's what I'm using it, which I'll keep on expanding now. So it should lead me to so now I open this, I multiply, like I open this, so I should get c square u square minus 2 cu times cu plus c square u square. Okay, which will further be written down as e of, so here look at this, I have c square common, right? So let me just take c out, c square is out, this becomes e of u square minus 2u which will be written as c square e of u minus eu the whole square. which is again C square of variance of U. Okay, that is that. And the last one is where U plus D. So variance of U plus D, again, I'll write it down again as I mean, this would just be like the variance of a constant is always 0. So it's going to be the same thing. Okay, so here just assume, like, just keep a note that variance of a constant is 0, and hence it doesn't really impact the random variable. Next up is given to it. So that's a question now. One more thing to note right there, just make a note of that, is the square root. I mean, this is something out from statistics, that square root of variance is called standard deviation. Okay. Next up is just a practice question from the textbook. You're given two independent random variables, x plus x and y, with the expected value of x to be 1, expected value of y to be 2. The variance of x is 3 and variance of y is 4. Find the variance of x and y. X multiplied by y. Let's do that question. So you can pause it, you can go out of it if you have already seen this question. I'll just do it and give you an intuition, like what is going on in that textbook example. So this goes as e of x square y square minus e of xy the whole square. Can you write this down? This is e of u square. This is essentially e. Oh, okay, I missed this. Where is it? Yeah. So this is EU square minus EU the whole square. This is what we wrote for variance. This is exactly what we're writing in this format. Now we know that E of x square y square can be written as E of x square times E of y square minus EX EY the whole square. Right? So now I write this down as, now E of x square can be written as, I already have the variance here, right? So that's why I'm going to use that. Variance of x plus E of x the whole square times, the same thing for y, variance of y plus E of y the whole square minus of EX EY the whole square. Now I have all the variables I need. Okay, just one more thing. How did I come up with this? So this also comes from this value, that where x, the variance of x can be written as EU square minus EU the whole square. And I have the value of EX square. So I just plugged it in here and I got it in terms of variance of x and the expected value of x. Okay. Just plug in the values of the four values given here. That is the expected values of x and y and the variances of x and y. And you can get the answer of the variance of x, y. Okay, just something to note here is the size of variance x. So variance, if it is like given that you have a variance of $1 in the data that you have, if you're talking about billionaires, then if we're talking about $1 billion, so if I'm looking at a particular household and all the houses here are $1 billion houses, then the variance doesn't really matter to me. But if I talk about the variance of a burger or anything that is very cheap, that is, let's say $4 burger, $3 burger. So here the amount of variance is very different. So it's always good to have a measure that measures the variance, but also relates it to the expected value, that is E of X, so that we know that if the expected value is like $1 billion, the variance doesn't really matter if it's $1. But if the expected value is like $2 or $3, then that $1 really adds up, right? Okay, and the other thing is, I'm sorry if I pronounce this wrong, but it's Chebchev's inequality. I'll just give you a small intuition what this means. This just means that if you, so there are C variation, C standard deviation. So this is the standard deviation. So for C, and this is the mean. Mean, this is the standard deviation. Okay. So what does this say is that X strays away from its mean by more than C times its standard deviation, at most 1 by C squared times. Again, this is the mean, this is the standard deviation. What I'm saying is that the random variable X strays away from the mean by C times the standard deviation, at most 1 upon C squared times, with the probability of 1 by C squared. So what the textbook does is, they have a really cool thing where they say that C is equal to 3. And then they say that X strays away from 3 standard deviation. X strays 3 standard deviations from its mean at most 1 by 9 times. 1 by 9, 3 standard deviations, and this is the mean. So X stays away from mean by a distance of 3 standard deviations, at most 1 minus 9 times. Okay. Next, next we look at what is covariance. Now, that's what we talked about, the dispersion in terms of the variance and the expected value. So let's write that down. That's right. Oh, that's right here. The covariance is a degree of the correlation. So that is the expected value of the product of the difference between the random variable and its expected value times the random variable, the other random variable from its expected value. Okay, so that's E times U minus EU times V minus EV. What you can do is you can really open this up. Let's write this down. Y is this particular format, also written as E times UV minus EU EV. So that is E times, we just multiply this. This is EUV minus VEU minus UEV plus EU EV. Okay, so now open this up. You'll have EUV minus EU EV plus EU EV minus EU EV. And these two cancel out, and you have EU EV minus EUV minus EU EV for that. So that's the covariance. I just derived that for you. That's how you write the covariance. And we can also write variance of U plus V as variance U plus variance V plus 2 times covariance UV. Just remember this result. Something else that you should remember is variance of, of AU plus BV is written as A square, the variance of U, plus B square, the variance of V, plus 2AB, covariance of U and V. So if there is if two variables, if the two variables are independent, they don't depend on them, the covariance is 0, and you can directly say that variance of U plus V is variance of U plus variance of V. Okay. This could help with your homework questions as well. Okay, next up is something called the indicator random variable, where it just takes a 0 or 1, whether it is defined, however the event is specified. Like if an event occurs, there are 2 outcomes, and it just is like based on 0 and 1. Okay, and let's say X is the random variable for A, then P is the probability for that event occurring, and the expected value for that random variable is P, and the variance of that random variable is P times 1 minus P. That is the probability of a success times the probability of a failure. Why do we write it as P? So let's just talk about that. So if we say that, what are the possible outcomes? It's 0 and 1, right? So the expected value will be sigma I Pi. So this is going to be 0 of Pi x is equal to 0 plus 1 times p of x is equal to 1, which is essentially, where did it go? Which is essentially 0 plus p. So that's that. All right, and variance can also be done the same way. Let's look at the question of returning the library book. I'll talk about that question and then we can solve it. This is a very initial question, like it's just superficially exposing you to indicator variables. Okay, so let's talk about this. At a public library, patrons return books exactly 7 days after borrowing them. So 7 days after borrowing them. It's never early or late, so it's exactly 7 days. But they can also return at another branch. So if they deliver at another branch, then it adds 2 days of the transfer back to this library. So it's 9 days, right? So there are just 7 or 2. And let t be the random variable that denotes the time taken to return the book. So t would be equal to 7 plus 2i, where this in random indicator variable, what does it do is, if you return it at a foreign library, then it is equal to 1, which means that you'll have to add those 2 delivery or the transit days into your total time. And if it is 0, then you have delivered it or returned it to your own library. Okay, and then you're also given that 50% of the patrons return their books to a foreign library, so 50% return it to their original libraries, right? So t is 7 plus 2i. Now when you write variance of t, you write variance of 7 plus 2i. So that's just 2 times. Oh, sorry, it's not 2 times. Let's look at the properties again. So if it is variance CA plus B, first of all, B doesn't impact. There'll be equal to variance of CA, which would also be equal to C square of the variance of A. Okay. So this becomes 4 times the variance of I, and the variance of I we know is P times 1 minus P for indicator variables. So that is 4 times P 1 minus P. Okay, and we know that P is 0.5, so that becomes 4 times half, that is equal to 1. Now, I would really want you to simulate this problem, and we can discuss over this in the OS, because if you're able to simulate this, you can really do indicator problems well. And I think I will also leave that discussion about the second question about returning time for library books in the next discussion, in the next week's discussion, so that we can loop back to this concept. Okay, next question is the committee indicator problem. Now this is a good question. So in this question, you're given that you want to create a committee of 4 people from 6 men and 3 women, and you want to take care of gender imbalance. So you just write gender imbalance as M minus W, which is equal to the difference, and you want to find the expected difference. So what is the expected gender imbalance? Now, this question has been solved in the textbook by both ways, where you identify the number of ways possible, like the expected value, like I times pi, the summation of that. And the other one is using indicator variables. So I'm just going to use indicator variables here. But if you want to discuss that, you can drop by now, officers. So E of D can be written as E of M minus W, where we know that M and W are the number of males and women, men and women selected. So we know that M plus W will have to be equal to 4. So W can be written as 4 minus M. This becomes expected value of M minus 4 plus M. So that is E of 2M minus 4, which is, so minus 4 goes out. You have E of 2M, so this becomes 2 of EM minus 4. Okay. Now, M can be said as, let's denote it by G1 plus G2 G3 plus G4, where GI denotes the indicator random variable for the event that the ith person is male. Okay, so the first person is male, the probability of that plus the probability of the second person being that, third and fourth person being a male. Okay, so the expected value of E of M, sorry, the expected value of E of M becomes EG1 plus EG2 plus EG3 plus EG4, which is essentially, because we're just talking about one person being picked, that is 1 times the probability of that happening each time. And you can fill this up. I'm just going to write it down as it is. What is the probability that G1 is equal to 1? So here I'll just write down G1 is equal to 1. This would be G2 equal to 1, G3 equal to 1, and G4 equal to 1. What is the probability that G1 is equal to 1? So I'll just write this down here. Number of men upon total people, total. So that is 6 by 9. So that is 2 by 3. So this becomes 1 times 2 by 3 will be added 4 times. So that's going to be 8 upon 3. So EM is equal to 8 by 3. Okay. And then E of D would become 16 by 3 minus 4. That is 4 by 3. So the expected difference is 4 by 3 here. Okay. This is how we did it. We first created the random variable here, D, that was M minus W. We found the expected value of D in terms of M. Then we found the expected value of male using indicator variables for each pick of the people, the G1, G2, G3, G4. We found the value of E of M, plugged it back in for E of D, and hence we found the expected value for the gender imbalance. Okay, so that was one question. The second question is pretty simple. This is the spin-off game, where person A spins a spinner, and that has a mean of 10 and a variance of 5. So okay, let me not write it down as that. Where the mean is 10 and the variance is 5. Person B flips a coin. If heads, oh, and also, so A spins the coin and gets S as the prize, which, okay, I made a blunder here. So S gets the prize, which is expected value is 10 with a variance of 5. If B flips a coin and gets a heads, then the person wins all the S prize of that A got. If it is a tails, nothing really happens. Okay. So what is the and so this is considered as T. So we all want to find the variance of T, that the prize that B wins. Okay. So that can be written down as variance of I times S, I being the indication of the flip of the coin. If it is a head, it is 1. If it is a tail, it is 0. And similarly, S is the prize that A wins in the first place. So again, it's the variance of X times Y, which can be written as, okay, let's write it down as, okay. If you remember this from one of the previous questions, variance of Y plus E, the expected value squared, times variance of S plus expected value of S the whole square, minus E of I, so the expected value of I and the expected value of S the whole square. Okay, and you can find the values here. You know the variance of E and the expected value of S here. You know you flipped a coin, so you know P is 0.5. and you know the expected value is P, and the variance is P times 1 minus P. So you can find the values from this equation that we've written down right here. Okay, you know how to find variance of I and expected value of I. I just discussed it right here, so that should be okay. That is the mean, and the variance is P times 1 minus P of that arc. Okay, next one is the measurement of different ages. That's 3.11. I just write it down. So that is that you have to measure a boy's height at two different ages, 10 and 15. X is the height at 15 and Y is the height at 10. X is the height at 10 and Y is the height at 15. And you want to find the variance of Y minus X. And the question has a few options to choose from. Now you're not supposed to find exact values, but what they're giving is the variance of Y minus X is equal to variance of Y plus variance of X. Now they have a few questions. It could be plus minus, it will be greater and equal to. Okay, greater than or less than. Okay, so for plus minus all of them, which one of them is true? So let's write this down. Again, understand this. X and Y are random variables, but Y is heavily dependent on X. Okay, so the correlation is strong. Now we can write, we know that Y minus X is the variance of X, variance of X plus minus X, okay? Which can be written as variance of Y plus variance of X. Now make sure you know this. This is A, this is B. So A is equal to 1, B is equal to minus 1. And I have written this down earlier that variance of AX plus BY is A squared variance of X plus B squared variance of Y plus, and plus 2 times AB covariance of X comma Y. Now look at this. B is minus 1. So minus 1 squared will remain 1. So you're just going to write 1 here. This is 1. A squared is 1. But here it turns out to be minus 2AB covariance of X comma Y. Now the covariance is positive, and hence this value is less than variance of Y minus X. Okay, so what is the true answer? Variance of Y minus X is less than variance of Y plus variance of X added individually. Okay, just one thing to note here was the values of AB, where B was -1, which made it minus 2 times AB, the covariance of X comma Y. Okay, the bus ridership problem, I'll just go over this again because I've already went over this I think in discussion 2. So the bus ridership problem was simple. You had a bus that was going around. Initially, it had 0 passengers. But then at every step, a passenger got down with a probability of 0.2. 0 passengers got on with probability 0.5, 1 with probability 0.4, and 2 with 0.1. Bus is empty when it arrives at the first stop, but it is huge, so it can fill any number of passengers they want to get on. And Li denotes the number of passengers on the bus as it leaves the first stop. Okay. So Li is the number of people who leave the bus at the ith stop, and Bi depict the number of people that board the bus on the ith stop. Okay, so I'll just write that as leave, and Bi as board at ith stop. All right. So what we're supposed to find is the variance of Li here. L1. Let's just do L1. That's in the textbook. This can also help you with your homework question where you're supposed to find the variance of L1 and L2 and the difference of L1 minus L2. Just make sure you know what you're writing as variance of L1 minus L2, which would be done from this question right here. L1 minus L2 will give you the same thing as, okay, that's exactly what it should be and nothing more than that. Okay, so variance of L1 can be written as, from the equation, as E of L1 square minus EL1 the whole square. Okay, now let's find the expected value of people leaving, which would just be equal to P times, that would be I times PI, like the summation of that. So that will be 0 people leaving, 0 people getting up would be 0 times 0.5, 1 times 0.4, 2 times 0.1. Okay, and EL1 will be equal to E board 1. So the number of people getting on the bus is the same as the number of people leaving the bus. Okay, and EL1 square would also be equal to EB1 square, which is point, so that would just be I square PI, P of I. Sorry, let me just write that. I squared P of I. This is E of L1 square. Okay, then you can find the values of variance of Li. All right, next up is distributions. Now this is a simple thing. You were finding E and you're finding P of I. That's essentially a distribution. So if I say that X is the number of dots one gets in rolling a die. So the probability of getting 1 is 1 by 6, 2 is 1 by 6, 3 is 1 by 6, 6 is also 1 by 6, right? So the distribution of X will be of the form 1 comma 1 by 6, 2 comma 1 by 6, sorry, 3 comma 1 by 6, 4 comma 1 by 6, 5 comma 1 by 6, and 6 comma 1 by 6. So that's the binomial distribution of the random variable X, where X takes the number of dots on that you get on rolling a die. Okay. Probability mass function is denoted as P of V. So P of V can be written as P of V equal to K for any value of K in the support of V. So let's write it down. If you toss a coin until you get the first head, so that probability would be 1 by 2 raised to K, where K occurs. So this is coin tossed until first head. So the probability that it occurs on the first one is half. The probability it occurs on the second one is fail, and then you succeed. Or 3 is fail, fail, succeed. The fourth one is fail, 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 succeed. The probability of failure is half. So this becomes half times half times half, right? So that's 1 by 2 raised to 3. So essentially, this is the probability mass function for the coin tossed until the first head. And similarly, if you were supposed to find the, so that's probability mass function actually. Let's leave this. And the last thing that I want to discuss was the Watts-Strogatz random graph model. Now I'll just talk about what the graph model is, and then you can further talk about the probability distribution. So the first thing is you're given a graph of n nodes. And all the nodes are actually connected in a circular fashion. So there are n nodes already, right? And let's say n nodes, and there are n links then. That connect the nodes, okay? Now I give you 6 more links to add. K more links to add, K. So now these would, initially what happened is, if there was one particular node, if this wanted to communicate to this node, it had 2 options to go through, like either ways, right? But now these K more links that are added would act as shortcuts. So if there is a K link between these 2 nodes, this acts as a shortcut. Or like if there is a link here and you want to communicate with this node, there gets another shortcut, right? So you add K more links. Now, what are the possible number of ways you can add those nodes? or let's find the number of ways that there would have been n no. What are the possible links that could have been added for n links? So if all of them were connected, that would be n times n minus 1 by 2. All the possible links when there are n nodes, right? And now there are existing n nodes already, n links already. So if when I wanted to add these k links, then what were the possible places I could have added them, right? That's going to be these potential links that were there. I'll go over this again once. When you're given n nodes, what are the number of ways you can draw links? So if this node is right here, so I want to connect this node to this node. So there are n minus 1 ways I can connect this particular node with. Okay. So this is for one of them. Now, if I look here, what are the number of ways I can connect it to? So it goes on n times, right? But then since the links are bidirectional, the total possible links I can add was n times n minus 1 by 2. Okay. Now, if I'm saying that there are n nodes and n links already existing, the number of ways I can add those k more links was the total number of links possible minus the links already existing, which would have been n square minus n by 2 minus n, which is equal to n square minus 3n by 2, which is essentially n minus 3 by 2. Okay. So now my choice is basically from these n minus 3 by 2, I will be choosing for the k values. So now I'm saying that the random variable would be m, which is the degree of the node, degree of each node. And we want to calculate the degree distribution of m. So let's look at the probability that a node has r links. So PMR is the probability of the node has r links. Okay. Now, how can the node have r links if I want to add those k links? It already has the existing 2 links, right? So that's like, if I'm talking about this node, I want this node to have r links. 2 of them are already there. So what is the probability that those k that I added will be added to this node? Okay. So PMR is actually the probability that r minus 2 of the k new nodes, k new links attached to that particular node. So that would just be of the case that r minus 2 are selected in, so this would be like from n minus 3, I choose r minus 2 values times these ones. So that is n squared by 2 minus 3n squared by 2 minus n minus 3 that have been chosen already. K minus r minus 2 are chosen out of that. So this is choosing the r minus 2 links for this particular node, and these are for the other nodes that are existing out there, divided by the number of ways you can just choose all of them. So that is going to be n minus 3 by 2, choose k new links. Okay. So this is the number of pairs you choose. So this is the probability distribution for the random graph model. And that is it for the conceptual parts of this discussion section.